Jonas, you work at Blockstream, right?
Yes,
What do you do at Blockstream?
I work in the cryptography group, and we do all kinds of cryptography for Bitcoin. In the past, we spent a lot of time working on various types of signature schemes,
Okay.
like music too, frost, aggregate signatures.
Does anyone ever say that's music to their ears?
I've heard that before, yes. It's
What
a
is
good
it?
one.
Okay, what does it mean to be a cryptographer though? So you work on signature schemes. We can come back to that. But like, what is like your day-to-day work as a cryptographer? You know?
Yeah, as my colleague Tim likes to say, we are full stack cryptographers,
Okay.
meaning that we produce papers and we publish them in academic settings, peer-reviewed, etc. So that's provable cryptography, where you have some sort of cryptographic scheme, for example, a signature scheme,
Okay.
and then you prove its security. And then we also write specifications, BIPs in the Bitcoin world, Bitcoin improvement proposals, that detail how exactly you would implement those schemes, defined down to the byte level, and defined in a way that makes it hard or difficult to misuse. And then we we implement these schemes in our various libraries.
That is full stack. So
That's
you're
the full
so
stack.
you're a theoretical. You do the theory part of like this is how these people should coordinate to achieve a goal, right? Like sending messages privately or creating signatures, right?
Yep.
And that's the paper writing part.
Yep.
And then okay, we've written the paper. Now, how do we like actually translate the paper, which are usually more abstract, right?
Yeah, yeah.
It's like a
They
general
use-
blueprint.
Right, they use these mathematical objects, generators, groups, etc., and you need to translate them into into bytes, right?
Right, and that's the bit process, right? Is like here's how we're
That's the bit
actually
process, exactly.
practically with bits and bytes and
Yeah.
like exact precise messages going to make this protocol that
Yep.
I've designed happen.
Yep, exactly. And the BIPs, they should also, or our BIPs, they have like very extensive test vectors,
Okay.
such that if you implement it and the test vectors they pass, then you should have high confidence that you're actually implementing the
That's
right
cool.
thing.
That's really cool. I mean, that takes a lot of work, right?
That takes a lot of work, a lot of thankless work. BIP writing is
Well, thank you. Like, this is a good opportunity. Thank you for all that work. So one of the more famous, and then after you've written the BIP, you go ahead and you implement it into. Do you implement things into libsec P256K1?
so. For example, like libsecp has music
Yes.
since I believe since last year.
Did it get added? Was Jesse Posner working on that, or no? He was working on Frost
He's
stuff.
working
My
on
bad.
Frost, yeah.
Okay, you did the music
Yep.
to implementation.
Yep.
Okay.
Me and a couple of other people who spend a lot of time reviewing it.
Yes, I remember seeing emails about review time. Like
Yeah.
it took you guys a long time to review it, right?
Yeah, yeah. So that's also a little bit of the down. I mean, as in every software project, like you need to find reviewers, but they are busy with other things, so they review your stuff. But if you want to address the review, then you are busy with other stuff. So it's like it just takes a while.
Takes a long time to get coordinated because it's async
Yeah.
communication, right?
Yeah.
Okay, so you worked on one of the BIPs. Like maybe a good example of this is you worked on the Taproot BIP, right? Mm-hmm. Was that? Would you consider that kind of part of the Did you do like the cryptography part for that? For like, what was the crypto work on the Taproot BIPs?
Yeah, to be honest, like my contribution there was mostly helping with the reference implementation and the test vectors and making sure that the BIP is understandable. But like sort of the cryptographic foundations, I think they had not been proven at the time as at which we wrote the BIP.
You said you did it later.
I would say at least some parts that happened later. For example, the Taproot BIP says, or the Schnorr BIP, which the Taproot BIP is based on, it says, for example, well, you can use music and Frost with this, but like the combination of music and Taproot, that was not really proven. We just assumed it was secure. It's a relatively maybe not a straightforward argument to make in a mathematically rigorous way, but it would be unlikely that this would be broken.
And now that you've done music too, do you have the proof? Did you later do the proof that it wouldn't be broken?
With Taproot? No, not really.
Okay. It's like, I don't, wait, does that mean what does it mean that you haven't done the proof yet though? Is it, people still lock money up to it, right?
Right. I mean, this is a very specific part of music, right? Because in music, everyone sort of generates their own secret key
Oh,
from
I see.
randomness, right? But in Taproot, you're not necessarily doing that. You generate your secret key, and then you tweak it, right, to get the Taproot tweak, and
Right.
then you sign for that. So that is sort of the difference.
Slightly different. And so Music, there was an original version of Music, and you guys ended up coming up with Music 2.
Yep.
The second one, Music the second. Is that
Yep,
because
Music
there
2.
was something with the first Music that didn't work with the Schnorr algorithm that you guys used in Taproot?
No, the history was just that we implemented Music 1, and that took quite a while because Music 1 requires 3 rounds of communication, and sort of your state space of things that can go wrong explodes the more communication you have between the signers. But then Tim essentially came up with a trick to reduce the rounds of communications to 2 only, which simplifies the implementation quite a bit, and also the API, right? So using it is much easier than using Music 1.
That's nice. So really it should be called Music 3, the first one. So it's 3 rounds of communication, and then Music 2 only has 2.
Yeah,
We don't do that with things,
no,
but yeah,
it would
okay.
be a bit confusing.
It would be
perhaps.
quite confusing, yeah. But that's what happened, right? It went from 3 rounds to 2 rounds on the
Yes,
newer
yeah,
version.
I would say that's the main difference. A couple of small ones, but not really.
How much of your job is around like finding tricks?
Ooh, that's a good question. I think tricks are a big part of it, right?
Right? I feel like that's the memorable part of the cryptography stuff. Like new papers and stuff, I feel like come out when new tricks are discovered.
Right. This would be what we are doing, I
Okay.
think, because we are looking at the Bitcoin space and our problems that we have very specifically. But there's, of course, also the other approach where I have a trick
Okay.
and now I want to apply it to all these different domains, which is also what people do in cryptography.
Got it. Okay. So you're very focused on the Bitcoin space. Like
Yeah.
you're probably, I mean, I would bet you're probably one of the top cryptographers in Bitcoin as a specialty.
There are quite a few people who do sort of blockchain stuff and related stuff, also related to Schnorr signatures, that are useful in Bitcoin, but they are not, I would say, they are not in communicating as much with the Bitcoin community as we do. Like they don't write BIPs, they don't write mailing list posts, etc.
So you guys almost then become like a conduit for outside research into Bitcoin, maybe?
Yes, I think that makes sense for us as Bitcoiners if we take the best ideas from cryptography, and like even if they don't maybe promote it enough in our space, then someone else needs to do that.
That's cool. So what have you been working on? So like Taproot and Music 2 stuff is pretty far in the preview mirror, right? Like you shipped implementation, it's a BIP, it's been launched, it's been, Schnorr signatures are available on Bitcoin. It's kind of exciting.
Right.
That's sort of, I mean, congratulations, maybe, I don't know. What are you focused on lately?
Right, so recently we published on ePrint, so not a proper academic venue, we published a paper called Dahlias, which stands for Discrete Logarithm Interactive Aggregate Signatures.
Okay.
And one way to understand what aggregate signatures are is to look at the syntax of different signing schemes.
Okay.
Right? So you have single signature verification. It takes a public key, a message, and a signature. It outputs true or false. Then we have, for example, a multi-signature scheme that takes multiple public keys, one message, and a signature, outputs true or false.
List of signatures, right? One for each public key. Or is this like...
In music, this is
music,
just
okay.
this is just a syntax. So the signature might be a concatenation of multiple signatures.
Got it, okay.
Right? But ideally, you want to have a small signature. In music, we have constant size signatures that's independent of the number of signers.
That's cool. That's a nice trick.
Yeah.
Would you call that a trick? Being able to have a bunch of signatures, a bunch of pub keys, and one constant size signature.
Yeah, you could call it a trick.
Okay. Cool.
And then aggregate signatures, you take multiple public keys and multiple messages and a single signature. So that's different to multi-signatures. You have multiple messages. And then verification outputs, true or false. And there is the trivial aggregation scheme, we call it, where you have ordinary single signatures and you just concatenate them into one aggregate signature. It's not efficient. So we want to improve on that, right? If we want to actually build an aggregate signature.
So it's not constant size signature? Is that one way of saying it? Because it changes depending on how many people you have.
Exactly.
Okay.
This trivial scheme.
Right, okay.
Right. So now Dalias is the first aggregate signature scheme that has constant size signatures and works with Bitcoin's curve.
Cool.
Yep.
Oh, very cool.
So constant size signatures in our case means, so for Bitcoin's curve it would be 64 bytes, so it also looks very similar to Schnorr signatures.
Right, which are also 64 bytes.
Yeah, exactly.
That's useful, so you can kind of hide in the blockchain.
Not really, because the
okay.
syntax is different.
I see, okay.
Because it takes multiple messages, so you know which public key signed which message essentially, or approved or authorized which message. So yeah, and it works with Bitcoin's curve, meaning it's only based on the discrete logarithm assumption. There are existing aggregate signature schemes that are also constant size, but they require different curves. And Dalias is interactive, so similar to music, it's 2 rounds of communication. First round, you exchange some nonsense. Second round, you exchange the partial signatures.
Cool.
Right, so that is Dalias. And the paper is really only concerned about the cryptography parts. It has a small section in the introduction where we talk about applications, and the main application that we think about is cross-input signature aggregation, CISA. CISA is this old idea in Bitcoin where instead of having multiple signatures per transaction, one for each input, one for each output that you're spending, you only have one signature.
Wow.
For example, one signature per transaction, or even, it doesn't work with Dalias because it's interactive, it would be one signature per block.
That's insane. And what's insane about that is how much space you would save in the blockchain.
Yes, yeah. So in the very best case, you would save about 30% in bytes compared to an average transaction.
That's a lot. And that's just the transaction layer. We can't scale it to blocks with Dalias. But
Yeah, so what you could, in the optimal case that we're envisioning, block would be one large coin join.
Wow.
Just one large coin join transaction. This would be the optimal case.
Is that good for privacy then?
Not directly, but indirectly, because it incentivizes coin joins, right? Because if I make a transaction, one input, one output, let's say, I have to pay the fee for a 64-byte signature, right?
Right.
But if we together make a coin join, collaborative transaction, each provide one input, one output, then each one of us is only paying for half of the signature that is part of this transaction, because there's only one signature in this transaction, ideally, if we would use CISA. So we have this incentive to collaborate now.
That's cool. If you get more inputs, you can still cut down to a single signature, right? It doesn't matter. If you have multiple inputs, it's not just one input. So if you each had 2 inputs, you'd still only have one signature.
Exactly. Yeah. So it also helps for you don't have to do coin joins.
UTXO consolidation, though, all of a sudden is a much less expensive. That's cool.
Yeah. It's also easier to do then because the rounds of communication are only between yourself and you trust yourself to not do weird stuff.
That makes sense. Yeah, that makes a lot of sense. You can just do it on your own
Yeah,
computer really
yeah,
quickly.
it's all on the same, would all be on the same device.
Right, which is a lot easier, I think. Yeah, okay. So Dahlias is a paper. What's the next step for you guys? So you've published it. I'm assuming that putting on ePrint means you need peer review,
Yeah,
or
so we will submit it to a conference, I think, in October. So still some way out. But yeah, next step would be writing a bit for this.
cool.
I think so. There are some people writing and that are interested in writing a BIP. We are currently not focused on the BIP part of this. Like there are alternatives, I would say, to
Okay.
using this for Bitcoin consensus. One obvious downside of Dahlias is it uses Bitcoin's curve, which means that it's not secure against quantum computers. So it might be a little bit difficult in the community these days to make this big upgrade to the signature scheme without accounting for post-quantum.
Quantum
So
resistance.
that makes me a little bit uneasy because we know these things, they take a long time, right? It might take whatever, 5 years or something. And maybe in 5 years, like suddenly we all want post-quantum signatures, but now we have Dahlias. So we have this efficient scheme, but in order to actually get post-quantum security, then we have to throw it all away and then work with these inefficient schemes. And the other alternative, there doesn't really exist an alternative yet in the post-quantum scheme that would allow this type of efficient aggregation, but there is a scheme that is called half aggregation,
Okay.
which is very nice because it's non-interactive. So it's you have an aggregation algorithm that takes a list of Schnorr signatures and outputs an aggregate signature.
Cool.
And there doesn't need to be any communication. It's just a function from list of Schnorr signatures to an aggregate signature. The downside is that the aggregate signature is not constant size, so it grows with the number of signatures. It's about half the size of the sizes of the individual signatures.
Got it. Okay.
That's why it's called half aggregation.
So you get like a 50% reduction
Yep.
instead of, in the other one, it literally is like constant size. Yeah,
Yeah,
so,
yeah.
okay. That's really cool. Interesting.
Yeah, so that would be the other alternative, and it's also quite a bit simpler.
This episode is brought to you by BTC++, the premier technical conference series for Bitcoin developers. BTC++ is not your typical Bitcoin conference. It's a world-class gathering of engineers, hackers, and builders focused on the cutting edge of Bitcoin development. From protocol research to Lightning, smart contracts, covenants, privacy tools, and beyond, BTC++ dives deep into the work that's shaping the future of Bitcoin. Join us for our next event in Riga, Latvia on August 7th and 8th, focused on Bitcoin privacy, and see all our upcoming events across the globe at btcplusplus.dev.
Does the half aggregation stuff, does that lead into quantum security, or is it still kind of on the same, we would need
Yeah,
to
it's
fix
still
it?
Schnorr signatures, the half aggregation.
So like, I mean, since you brought up quantum as a cryptographer, what, like, are we gonna have to change the curve and like Schnorr signatures are going away to become,
Yes.
okay.
Yep.
That's a big
because
change.
That would be a big change. Yeah. I mean, it's for example the security proof of Schnorr signatures or of Dahlias just says that as long as, or if someone would break the signature scheme, then you would also be able to break the discrete logarithm assumption, which is sort of our curve, right? What is a discrete logarithm assumption? To put simply, it's just computing the private key from a public key.
Right. So being able to go backwards, you know what the
Yeah.
public key is, you can
Yeah.
figure out what the private key is, which right now is pretty difficult. It's brute force
With
only.
classical computers, as far as we know, it is difficult.
Brute force, right? I guess.
Yeah, they're a little bit clever algorithm, but still. And since 1994, we know that the discrete logarithm problem is not actually hard.
Interesting.
As long as you have this device, this machine called the quantum computer.
Okay.
So now it's just a question when to build this quantum computer. Like our security proofs, they are not magic. They're just saying, okay, we reduce this one problem, breaking the signature scheme, to another problem, breaking the discrete logarithm. But we don't know how hard it actually is to break the discrete logarithm.
I see. So a lot of the schemes that you've written for Bitcoin depend on this assumption that it's hard to break discrete logs. But everyone knows that quantum computers can do that.
Yes, yes. I mean, they call them cryptographically relevant quantum computers, so they need to have some size and qubits, etc.
Do you keep up with the quantum research at all?
Yeah, I try to do that now.
Okay.
A little bit more. It's hard to keep up. It's sort of pretty closed group and like lots of startups in this space as well as large players.
It's kind of noisy, right? Like it's hard to know what the real progression is.
Yeah, but there are some Bitcoiners who are really interested now in digging a little bit deeper into potential timelines, or what are the actual press releases and events that would be relevant for us. But I think even today it's something to keep in mind for the future of Bitcoin, because it makes me uneasy to write these sort of proofs.
Right, interesting. That's interesting to hear, yeah. So like when you're working on proofs and stuff, how much time have you started, like as a cryptographer researcher, are you familiar with like what post-quantum cryptography looks like? How much like of your time are you spending doing research in post-quantum?
Yeah, I mean, I'm spending some time at conferences, and I know some people who are really deep into the topic, so I definitely try to keep up with what is going on there. And it is still a developing field, which is really interesting. Like there are these standardized signature schemes that exist, but these are the first ones that have been standardized. So there's now, NIST has a second round of standardization competition for signature schemes that are based on a little bit different assumptions, etc. But aggregation has not really been taken into account too much, I think, because like the usual application of these things is, of course, something like TLS, right? And TLS doesn't really need aggregation or multi-signatures. So we saw after we published Music 2, there were a lot of papers that were building something like Music 2, but in a post-quantum setting. And we hope that the same happens with Dahlias, where people in the cryptographic community, they realize that the signature aggregation is this really useful problem in practice. So let's figure out how to translate that into the post-quantum setting.
That's really cool. I mean, that's pretty cool if you're able to influence the future research that strongly.
Yeah, hopefully we'll see.
Yeah, so if you're listening and you're working on quantum stuff or in the crypto space, this is sounds like a fertile place to spend time and research. Where do new cryptographers come from? Like if people were interested in participating in this work or learning more about how to contribute to these fields, where's the avenues for entrance into doing this kind of work?
I think I think people should perhaps, I still like the Bitcoin mailing list.
Okay,
right? Because the Bitcoin mailing list, that is this collection of ideas, and I feel like it's still a creative place. So I think you can read some of the ideas there and try to improve on them, or try to formalize them. So that will be my recommendation, because like the Bitcoin mailing list, people come up with solutions or potential solutions to problems they care about, right?
Yes.
So this is what makes it valuable.
So it's valuable because it's very practical focused. It's focused on solving real problems that we have in Bitcoin.
Right.
Whereas like other cryptography is more like maybe what you mentioned earlier, where they find a trick and then figure out what they can apply it to.
Yeah, I wouldn't say all other cryptography is that, but that certainly exists. Yeah.
Yeah, maybe that's like a thing. Cool. Is there anything else we should know? Are there any conferences people can find you talking at, or like places to follow your work?
I may be going to BTC++ later this year. I haven't fully decided yet.
It'd be great to have you.
Yeah. Other than that, not really planning on a conference. Yeah. Well, you can follow us on Twitter, Blockstream Research,
There you
where
go.
we're posting our updates. I think that would be the way to stay.
And the Dahlia paper, if people want to read it, is on ePrint.
Yeah, it's on ePrint. Dahlias, right? Delta, Alpha, Hotel, Lima, India, Alpha, Sierra.
Wow, you remembered the like call tag for it. That's pretty cool. I'll try and remember to put a link to it in the post
I
as
need it
well.
for my name sometimes.
Really?
Yeah,
Oh wow,
hotel reception or something.
cool. Wait, that's the ePrint like tag, right?
No, that's just how Dahlias is spelled. So just if you want to
Oh, I
find
see.
Dahlias, go to ePrint
Sorry.
or Google ePrint Dahlias.
Got it. All right, cool. Well, thanks for your time, Jonas.
Yeah, this
Cool.
was fun.
Yeah, super
Thank you.
fun. Yeah.